All right, the last concept when it comes to bonding and Lewis structures is something called resonance. Now, resonance again is more of an organic compound concept, but it is something that is popping up occasionally in the national exam that I want you to be aware of. What resonance is that one Lewis structure does not show all the possible bonding that can take place in the molecule itself. And what usually, in order to see it, what you will notice is usually involves oxygen and carbon, but it doesn't always have to. But what you will see in a molecule is you'll see, for example, a carbon singly bonded to an oxygen, and then somewhere else it might also be bonded doubly to oxygen. And one Lewis structure cannot justify or show the whole structure, because who's not saying that the oxygen on the right couldn't have the double bond and the oxygen on the left has the single bond? So what you have to do is you have to draw multiple Lewis structures that shows that single and double bond switching positions and places. This is resonance. Resonance means to go back and forth, to resonate back and forth between. So that double bond, okay, might jump into this side and go back and forth. So the double bond is going back. Now it has, in order to be resonance, it cannot show a different structural arrangement. So we can't have a carbon bonded to a nitrogen and then doubly to an oxygen, and then we flip-flop back and forth. That single and double bond must be flipping back and forth between the same two bonded atoms. So it must be carbon to oxygen and carbon to oxygen. It can't be between carbon and oxygen and then carbon and nitrogen. That would be a different bonding arrangement within the structure itself. So resonance, what you're looking for is usually a central atom in which you have multiple oxygens probably coming off of it, and that double bond can flip back and forth between one oxygen and another oxygen. Okay? So a couple years back on the national exam, they gave a box, and on it they said one Lewis structure is not enough to show the bicarbonate ion, HCO3-1. Draw all the possible Lewis structures to show all the possible bonding arrangements. All right, so if we have bicarbonate, which atom goes in the middle? Well, hopefully you decided on the carbon. Carbon almost always goes in the middle. All right, we have three oxygen. I leave hydrogen always at the end. We can always put hydrogen last. So I'm going to put the oxygens. And we always single bond first to develop it's called the skeleton framework. There. Okay, now you're going to want to be tempted to put that hydrogen off of that carbon, but that's not what happens with the bicarbonate ion. Okay, the hydrogen actually goes off of the oxygen. Now, why would that be? Because there again, we should know from past unit that bicarbonate has acidic properties or basic properties, and that's due to the fact that we get this OH group where that hydrogen could be pulled off, okay, making it an acid. It's a proton donor. Okay, so then the two other oxygen, the oxygen and carbon, one of these bonds could form a double bond, which means now these two guys right here are gone, eliminated. Okay, and which now means don't forget there's a -1 on it. Whenever you have a -1 on a molecule, that means there's one additional electron that is going to be accounted for from the environment. We have to add one more dot, and we can see the place we need to add a dot is that bottom oxygen, which means now because it's gained an electron, not sharing, but gaining an electron, it develops a formal charge of -1. All of the other carbons and oxygen, we check the formal charge. Carbon should own 4 electrons, 1, 2, 3, 4. There's 8 electrons around it, half of which are owned by carbon. So again, if you remember formal charge, 4 minus 1/2 of 8 gives me a formal charge of 0. So whenever carbon has 4 bonds on it, it's always going to have a 0 formal charge. There's no charge on it. When oxygen never has 2 bonds coming off it in 2 lone pairs, these guys right here are also got 0 formal charge because they've got 2 bonds. But the other oxygen has a formal charge of -1 because it has gained 1 more electron. And if we look at formal charge, oxygen should own 6. Well, here it has 3 lone pairs of electrons, which is already 6, and there's also a bond formed between the carbon and oxygen, so there's 2 electrons there, which we times by 2. There's 2 electrons times 1/2 gives me one of those electrons is theoretically considered part of oxygen shell. So we have 6 minus 7, which gives us a formal charge of -1. Just a good little review of formal charges. So the only element here that has a formal charge is the oxygen. Okay? So now how many different possible Lewis structures could we draw with that? Well, in this case, we could now place the double bond off of the bottom oxygen and there would be the other resonant form of the bicarbonate ion, where that double bond is flipping back and forth between the single and the oxygen. So the easy way of identifying resonance is where you have an atom bonded, usually to oxygen, but doesn't have to be, maybe nitrogen, but it's usually oxygen, where you have a single bond between them and then you have a double bond between them somewhere else. And that means we can position the double bond and single bond at different locations. We are not changing the overall bonding arrangement of the molecule, just its location. Okay? All right, so let's turn the page then. A couple other examples here is a very common compound is benzene. Now benzene you can see actually is a cyclic ring, and this is more involving with organic chemistry, but I wanted to show that in benzene we have an alternating double bond and single bond. And there's one hydrogen coming off of each of them. So the other Lewis structure, this would be just to position the double bonds and flip them to their other locations. And we'd have hydrogens coming off the backside, off of each of the carbons. So this would be the resonant structures or drawings for benzene. And the way that we show that they're going back and forth is we draw a double arrow, double-sided arrow, which means they go back and forth, and that double bond flips locations. And this again is an example of showing resonance, where we see that alternating single. Now in this case we don't have any oxygen, we have just simply carbons single bonding to themselves and double bonding to themselves and just flipping their locations. Okay? And just for organic purposes, what we do in organic is we draw the benzene molecule in its hexagonal shape, because that is what it is, and then a circle in the middle. And that circle in the middle indicates that that double bond is rotating around and around and around, in essence cyclic. And this is exactly what organic chemists, how they draw the molecule benzene. This symbolizes all of that bonding as a shorthand way of drawing it. So if you see a hexagon with a 0 in the middle of it, a circle in the middle of it, that really is the symbol or symbolization of the benzene molecule. One other common thing I want to show you is the molecule ozone. So ozone is 3. Now, ozone is not a cyclic ring. I would not be considered at all with any cyclic rings. Don't think that way. If you have only 3 atoms that have only 3 or 4 atoms can never form rings in 3 or 4s because of the torsion on those bonds is so strong, the tension and all the electron repulsion, that these type of shapes don't exist. So whenever you have 3 or 4 atoms, never think of a cyclic ring. You got to have at least 5 or more. Ozone, when we draw it, we start off drawing it initially as a straight line like this with all of its electron dots, single bond between the 2 oxygens in the middle there. This is why students want to draw or make it a triangle. They want to just bring these oxygens together and bond there and make it just into a cyclic ring. But that's not the case when it comes to ozone. Actually what happens is one of these electrons moves in along with one of the other ones. They move in there to form a double bond. Instead of now doing it the same to the other ones and forming 2 double bonds to each side of the middle oxygen, if I did that, we would end up having a total of 10 electrons. And remember, carbon, nitrogen, and oxygen and fluorine Never violate the octet rule. Always draw them with 8 valence electrons. So with that, this has got 10. You would not form 2 double rings. So instead, this electron is donated to this other oxygen here. And because one is giving them up and one is taking them, the middle oxygen develops a positive charge and the outside oxygen develops a negative charge because that oxygen has given that electron to the other oxygen, developing formal charges. So to clean up this molecule of ozone, this is what the ozone molecule looks like. Now, what geometric shape does this molecule have? Because of the lone pair in the middle, this is a bent molecule. Ozone would look like this in real life, where it's bent because of that lone pair coming off the middle oxygen, forming, in this case, a 120-degree bond angle between each other because there's 3 electron domains. Okay, but we call it bent because we cover up the lone pairs and we see a bent V from the 3 atoms, which gives a bent structure. Now, can this molecule have resonance? Again, the answer is yes, because that double bond could very easily have gone to the right versus the left. And so this would be the 2 resonant forms of ozone. So resonance could be the same atoms to themselves, or it could be like carbon to oxygen, but what we'll have is we'll have a single bond coming off one direction and a double bond between the same elements on another side, and we can just simply flip-flop their positions. Most common, you'll have 2 resonant forms. You can get as many as 3 resonant forms. A great example that would be the carbonate ion, where you can actually draw the carbonate ion 3 times because there's one double bond and there's 2 single bonds. So the double bond could be located to any of the 3 oxygens, and so we would then have 3 resonant forms. So that's one you could definitely try, and even look up on Google, search it, show all the resonant forms of the carbonate ion, and there you go. That'll give you what you all need for this this concept. So go back now to your tables. All you've got to do is put yes or no. Does resonance exist with a compound? Does it not? And again, it's pretty easy to identify. If you have the same type of bond, if you have a single bond and a double bond between the same type of atoms, okay? A carbon-oxygen single bond and you have a carbon-oxygen double bond, and you can just easily flip-flop them without changing any of the other bonding arrangement, just flipping the single double bond between the same 2 elements. That's a resonant molecule. All right, if you have any questions, again, just shoot me an email. Thanks for listening.